Hi guys, my name is Alfie Haider, and this is my small presentation on exoskeleton modeling. I'm gonna go over the agenda. At first, we'll have the mathematical exoskeleton modeling. We'll have the comparison of the actuation paradigms. We have the simulations by Simulink, and in the end, I will talk about what I learned from this course. First, what is exoskeleton? Exoskeleton is the stiff structure usually on the outside of living beings, which protects the internal organ. But in terms of for this class, exoskeleton is the structure that we attach to muscles and which replace some of the external organs. It's usually these external exoskeleton are usually used by people who has fractured different organs like legs or knee or arms, and the main purpose of this exoskeleton is to allow human beings or living creatures to live like a normal person, as if like nothing happened to those organs, and replace the functions of those organs using mechanical equipments. This is a picture of the exoskeleton. And on the left hand side, you'll see someone wearing the exoskeleton, and on the right hand side, you'll see a top view of the exoskeleton, labeling all the different components and also giving the dimensions to different components as well. So for this exoskeleton modeling we're talking about, we have three crucial components. The first one is quasi-direct driven actuator, second one is transmission, and third part is wearable structure. So what is quasi-direct driven actuator? It's the most important part of the project, and it's an actuator with a high density torque motor and a low inertia leg with low gear transmission. This is the modeling that we have for exoskeleton. You see on the left hand side, it's the quasi-direct drive. It's the part where the actuator goes on two different functions, electrical function and mechanical function, and then the mechanical motion obtained from the actuator moves into the transmission, and from transmission it moves into the wearable structure, which allows the person wearing it use their leg or use their hip to do regular gait cycles. This is the formula I obtained by using Laplace transformation of the formulas from the previous slides, especially for bandwidth. And yeah, this is the block diagram that we will be using for our simulation that we will see in the later part of the presentation. And this is the transfer function that we'll be using for our presentation to calculate our bandwidth for the actuator. Similarly, for the exoskeleton, for the back driver, we use the same type of mathematical modeling, except in the actuator part, the initial velocity is 0, but the other parts pretty much remain the same. And this is the block diagram that we will also be using in our Simulink for simulation. And this is the transfer function that I derived by using Laplace transformation on the formula of the previous slides. So let's talk about the comparisons. So there's a huge trend. So in general, in this type of exoskeleton, one of the other commonly used actuator is a series elastic actuator, but there's a good difference between series elastic actuator and the quasi-direct driven actuator. The first difference is in the structure, because series elastic actuator has small gear ratio, whereas the quasi-driven directed actuator actually has a larger gear ratio. Also, so the quasi-direct driven actuator also has small torque motor, which makes the whole structure of the exoskeleton very compact. The compliance durability and bandwidth is also high comparatively. The mass is low, which is a huge factor in terms of making the exoskeleton, and the stiffness is medium. Yeah, so these two parts, the mass and stiffness, it allows the exoskeleton to be very flexible, and also it allows the exoskeleton to be very user friendly for the user. So now we're gonna move into the simulation part of the project. This is the bandwidth block model. We already showed the mathematical block model. Now this is the block model that we used in MATLAB Simulink. And these are the two board diagrams we got for SEA and also the QDD actuators. Similarly, this was the backdrivability block model that was provided to us by Professor Hausu. And also, I also showed you the hand-drawn mathematical block diagram in the previous slides. And this is the board diagram of the quasi-direct driven actuator and the SEA actuator at the same time in this board diagram. Analyzing both the Simulink simulation, we see that the bandwidth value of QDD and SEA was 110.6 hertz and 6.31 hertz respectively. And in terms of backdrivability, the amplitude value of QDD and SEA was 4.3 nanometer and 4.2 nanometer respectively. So it pretty much proves our point from the comparison slides that QDD has more bandwidth and backdrivability compared to SEA actuators. So some of the learnings that I learned from this course. First thing I learned about is exoskeleton modeling, which I was very interested about before coming to the project, before registering for this course, because I was really curious about robotics, and this is one of the course which is an introduction to the robotic science. We learn about different actuators, especially the quasi-direct driven actuator, because very high drivability and high bandwidth with very low mass. And Professor Hausu was promoting this actuator a lot, so I learned about it a lot from his slides. Introduction to Simulink is one of the most important things as well. I learned a little bit about Simulink in my previous semester with Professor Howard, but now I was really curious on how to use Simulink in terms of gaining actual values from a real life project. So this is a project that allowed me to learn about those as well, and also the use of Laplace transformation to the derived transfer functions, because transfer function in the end allows me to set up the block diagram which we use in Simulink. So Laplace transformation, which we had an introduction to it last semester with the Mechatronics class, but this course allowed me to use it in real life project. Yeah, and that's pretty much it. So thank you so much for seeing my presentation.